In 1940, the Tacoma Narrows Bridge began to twist in the wind. What started as a mild oscillation quickly turned violent. Within hours, the structure tore itself apart and collapsed into Puget Sound. The bridge had been engineered, it had been calculated, it had been reviewed, and yet it failed. Decades later, a commercial aircraft suffered explosive decompression when metal fatigue weakened part of its fuselage. Again, the system had been engineered to establish standards. It had passed inspections. It met its design criteria. So here is the uncomfortable question. If engineering calculations are correct, why do we still need margins of safety? And perhaps more importantly, how much safety is enough? A margin of safety exists because reality does not behave like an equation. Every formula we use in engineering is a simplified model of the world. Those models are powerful, but they are never complete. Materials vary, loads fluctuate, manufacturing introduces tolerances. Human behavior is unpredictable, environments change. Over time, even well-designed systems degrade. At its simplest, a margin of safety is the buffer between the maximum stress a system is expected to experience and the stress that would cause it to fail. Engineers often express this as a safety factor. If a beam can withstand 10,000 newtons before breaking, and the maximum expected load is 5,000 newtons, the safety factor is 2. In other words, the structure can theoretically handle twice the intended load before failure. But that simple ratio hides a deeper truth. The expected load is not a single fixed number. It is an estimate based on assumptions. Consider a bridge. The load includes not only the weight of vehicles, but also wind forces, thermal expansion, braking forces, vibrations, and long-term corrosion. Traffic patterns may increase over decades. Trucks may become heavier. Climate conditions may shift. What was once a reasonable maximum load can quietly evolve. Even material strength is not a single number. Steel produced in different batches can vary slightly in composition and microstructure. Concrete strength depends on curing conditions and aggregate consistency. Manufacturing processes introduce variability at every stage. No two components are perfectly identical. Margins of safety exist to absorb those uncertainties. In mechanical and civil engineering, safety factors are often relatively high. Pressure vessels designed under ASME codes may use safety factors of 3 or more, relative to ultimate tensile strength. Bridges often incorporate conservative load assumptions. Buildings in seismic regions are designed to withstand forces well beyond typical daily stresses. In aerospace engineering, however, safety factors are usually lower, often around 1.5 for structural components. That might sound risky, but aircraft operate under a different optimization constraint. Every kilogram of extra structure increases fuel consumption and reduces payload capacity. Overbuilding an airplane is not just inefficient. It can make the entire system economically unviable. Instead of relying solely on large safety factors, aerospace engineers combine moderate structural margins with extremely rigorous analysis, advanced materials testing, redundant load paths, and strict inspection schedules. In other words, lower numerical margins are compensated by tighter control of uncertainty. This highlights a critical principle. Margins of safety are not universal numbers. They are context-dependent decisions shaped by economics, physics, regulatory frameworks, and acceptable risk. To understand this more deeply, consider how loads are categorized. Engineers distinguish between static loads and dynamic loads. A static load might be the weight of equipment resting on a platform. A dynamic load involves motion, acceleration, or impact. Dynamic loads can amplify stress beyond what simple static calculations predict. A sudden gust of wind can produce forces significantly higher than steady airflow. A moving vehicle crossing a bridge can induce vibrations that momentarily increase stress. Because dynamic effects are harder to predict precisely, safety margins must account for them. Another layer of complexity comes from fatigue. Even if a structure never exceeds its yield strength, repeated cyclic loading can initiate microscopic cracks. Over time, those cracks propagate. Eventually, failure can occur at stress levels far below the material's original capacity. This phenomenon is why aircraft fuselages are inspected regularly and why rotating machinery components are assigned fatigue life limits. A static safety factor alone cannot prevent fatigue failure. Engineers must analyze stress cycles, estimate crack growth rates, and incorporate inspection intervals. Margins of safety in this context are tied not just to strength, but to time. Now consider extreme events. Earthquakes, hurricanes, and floods are typically modeled using statistical data. Engineers might design a building to withstand a 1 in 50 year storm or a 1 in 100 year earthquake, but rare events can exceed historical precedent. When that happens, even well-designed systems can fail. This reveals a fundamental limitation. Margins of safety are based on probability distributions, not certainty. They reduce the likelihood of failure within expected conditions. They do not eliminate risk under all conceivable scenarios. There is also an economic boundary. If you attempted to design every structure with a safety factor of 10, costs would skyrocket. Materials would increase. Foundations would need reinforcement. Transport and installation expenses would grow. In many cases, the added weight would introduce new stresses elsewhere in the system. Engineering is not about maximizing safety at any cost. It is about optimizing safety within practical constraints. Consider nuclear power plants. Structural components incorporate substantial safety margins, but the system goes further. It uses defense-in-depth strategies. Multiple cooling systems exist so that if one fails, another can take over. Containment structures are designed to isolate radioactive materials even if internal components malfunction. Automated shutdown mechanisms activate if certain parameters exceed limits. Here, safety is layered. Margins exist at the material level, the system level, and the operational level. In contrast, consumer electronics often operate with very small structural margins. A smartphone case is not designed to survive extreme impact. It is designed to function within normal usage conditions. The acceptable risk threshold is different. Ultimately, a margin of safety is a structured acknowledgement of ignorance. It admits that models are incomplete, measurements are imperfect, and the future is uncertain. Rather than pretending uncertainty does not exist, engineering incorporates it quantitatively. When failures occur, investigations often reveal that the margin itself was not absent. Instead, assumptions were flawed, loads were underestimated, environmental conditions changed, maintenance procedures were not followed, degradation progressed unnoticed. The margin was consumed gradually until nothing remained. This is an important conceptual shift. A margin of safety is not a permanent shield. It is a finite buffer. If real-world conditions push beyond predictions repeatedly, that buffer erodes. Understanding margins also changes how we think about over-engineering. Adding material blindly is not the same as improving safety. True safety comes from understanding where uncertainty lies and addressing it directly. Sometimes that means increasing thickness. Sometimes it means improving inspection frequency. Sometimes it means redesigning geometry to reduce irregular stress concentrations. Sometimes it means implementing redundancy. The goal is resilience, not excess. So how much safety is enough? The answer depends on consequence. A garden shed collapsing is inconvenient. A bridge collapsing is catastrophic. An aircraft structural failure is unacceptable. The higher the consequence, the more carefully uncertainty must be managed. Engineering margins of safety are therefore not arbitrary numbers. They are deliberate decisions informed by physics, historical data, regulatory standards, economic trade-offs, and ethical responsibility. The next time you see a bridge flex slightly in the wind or an aircraft wing bend during turbulence, remember that movement is not failure. It is part of the design envelope. Engineers expect structures to experience stress. What matters is that those stresses remain within calculated limits, with room to spare. Margins of safety represent that room. They are the space between performance and collapse. They are the difference between a structure that survives decades of variability and one that fails under unforeseen strain. And most importantly, they remind us that engineering is not about eliminating uncertainty. It is about confronting it honestly, quantifying it rigorously, and building enough buffer to live safely within its bounds. If you value clear, research-driven explanation of how engineering systems really work, consider subscribing to Engineering Manual. Each video breaks down the principles behind the systems we depend on every day.